So here are the little homework boxes. You should circulate around. Okay. So the homework boxes are moving around, so make sure you just put your homework in the right little boxes. Any questions about the homework or anything? Okay. All right. Somebody asked about, let's see. You asked, was it the one with the 3 people? Right, is that? Okay, this is question 8 about restaurant A, restaurant B. Let's see. Okay, so there's 3 people, right? Each one we're feeding on A and B. Okay, then what is it? One is the most social person, right? Yeah, right. One wants to be social, yes? So What's the out here for 1? Just everyone goes A. I think the best thing. How about here? That's like medium, right? 5, yeah? So I think it's like this. Hold on, no. This is not, this is what? This should be 0, right?
Yeah.
That's where 1 gets is alone. This is 5, I think this is 5, 0, 5, 10. I think, yeah, especially 5. Yeah, kind of. Okay. All right. How about person B? Sorry, person 2. Person 2 wants the derivative to be as small as possible. Okay, so how about this for person 2? This is the worst thing, right? Similarly, like this is the worst thing for 2. How about this? This is the best, yeah. This is where person 2 is alone, right? Person 2 is going to be in the one going to 8. This is what? 5, right? Middle. This is what? 5. This is a 5. This is 5, but I think this is 10, right? Did I get that? Okay, person 3 wants to go to the same place as person 1. Okay. So how about here? This could have been good, right? What do you want to make it? 10. How about this? 10 also, right? But this is 0. This is bad. Okay. Did you get this? Yeah? Okay. Let's do domination. Okay? Let's see. Let's check whether for person 1 A dominates B. Okay, what I'm doing is I'm checking this versus this, this versus this, this versus this, and this versus this. Yeah? You see why, right? I'm only caring about person 1's numbers. Is the number from A always better than the number from B? No, right? 10 is better than 0, 5 here, 0 is worse than 10. Yeah? So A does not dominate B. Correct? Does B dominate A? No. Okay. If I were to check, now person 2, domination for person 2, I'm checking between this 0 and this 10, right? See, does B dominate A? 10 would have to be bigger than 0, the 5 here. So does B dominate A? No, right? Because 0 is worse than 10. I'm doing this kind of comparison. Yeah? Okay. So finally, let's do person 3. For person 3, I'm comparing this number versus this. And I'm seeing whether A is better than B and comparing this versus this. Does A dominate B? Well, 10 is better than 0. 10 and 0, yes, but 0 is worse than 10. Yes? Okay, is it clear? Any questions about that? So, do we have any domination in this case? No. Okay, let's use National equilibrium. Okay. Let's go to underlines. Okay, what's the best response for person 1 here between 10 and 0? 10, right? What's the best response between here? 5, 5. Best response here? 5 and 5. What about here? 10. Now, for person 2's best response is between 0 and 10. Is it clear why that is? Yeah, first of all, remember, person 2 only cares about the second number. Person 2 is choosing the column, so person 2 is choosing between this and this. Okay? So in this case, the bigger number is, and the bigger number here is 5. The bigger number here is 5. Bigger than here is 10. Person 3 is choosing between 10 and which is 0 over here, right? 10 is better. 10 and this as well. 10. 0 is 10 as well. 10, 0. So what are the Nash equilibria? There's 2. Right? Did you guys get this? Yeah? One is this one here. This is ADA. And PAD, right? Make sense? Okay. Any questions about that? Okay.
Yeah.
Yeah, no problem. Did everybody get this? What else? Okay. All right. So again, well, I was just practicing what to compare with what, and you just get practice doing it. Okay. Any other questions? Okay. This is homework 2, right? So there'll be homework 3, homework 4, and homework 5 before midterm. Okay. So still some time. All right. If you don't understand it, please just let me know. talk to me, talk to your TAs. You know, I'm around. I'm happy to talk about it. Okay. All right. Are we okay? Okay. Okay. All right. So what did we do? What did we do at the end of last class? Okay. How many ways do you have of making a prediction in a game? The first one was what? I just did it both. What's the first method? Iterative elimination of dominating strategies. Oh yeah, iterative elimination of dominating strategies. What's the second way? Nash equilibrium. Yeah. Okay. Are we done? We talked about this briefly at the end of last class. No. Why? Because we have this game here. Remember, this is a penalty kick game. Is there any domination in this game? No. Are there any Nash equilibria? No. Okay, so there's no Nash equilibria. What do we do? Okay, and so in this game, when we actually see people play this game, what do you think people actually do? They're randomized, right? In fact, you want to be as unpredictable as possible. Okay, so what we're going to do is talk about randomization. So we have our original game where you can either go east or west. Striker could either go east or west. But what we're going to do is we're going to add a randomized strategy. By 50-50, I mean half the time I go east, half the time I go west. Make sense? So throwing another strategy in difficulties. Make sense? Because it seems like in an original game, no one's going to go east all the time or west all the time, right? People are going to randomize, so I'm going to throw that in as a strategy. Does that make sense? What we're doing? No? People randomize, so get a bit randomization as a strategy. The only question then is, how do we put those numbers in there? Like, if I go 50-50 and you go east all the time, we have to fill those numbers. How are we going to do that? Yeah, it'll be 0.5. But how do we get those numbers? Yeah, exactly. It's kind of like expected overall things, right? Have you ever done an expected value calculation? You don't remember that, right? So that's kind of, well, let's talk about it. Let's talk about that. How do we fill in the payoffs? Okay, what we'll do is we have to take a little interlude. So this is a little bit of a side interlude, but we have to do it to make it work. The whole idea here is to figure out how do we write down payoffs of random things. Okay? So we're going to talk briefly about probability and expected value. Okay. All right. So what is probability? The probability of a random event is the likelihood it will happen. It's kind of tautological, but that's kind of what we're going to do. Say, yeah. Okay. A probability is a number between 0 and 1. There's no such thing as negative probability. Also, there's no such thing as, you can't say, I'm 120% sure that the Dodgers are going to win the next game. It doesn't make sense. Right? It has to be a number between 0 and 1. Okay, if you add up probabilities over all possible events, you get 1. Let me see if I can switch this off here. Okay, so for example, today there's a 20% chance of snow, 50% chance of rain, and 30% chance of no precipitation. Okay, like the weather report. So these numbers all have to add up to 1. Make sense? Right. So it's probability is a bunch of numbers between 0 and 1, and they all have to add up to 1. Okay. So let's give an example from roulette. Okay, this is a roulette wheel. Have you ever played roulette in a casino? I haven't. I've seen people do it in movies. Anyway, so what's the probability of the ball landing in like one of these given holes, like 26? Where's 26? Like that one. What's the probability the ball lands in there? Well, you have to count how many holes there are, right? How many holes are there? Well, there's 36 plus, there's actually the 0 and the double 0. So there's actually 2 extra holes. So there's actually 38 holes. Okay? This is in Las Vegas. If you go to Monte Carlo, there's only 1 green hole. So this is in Las Vegas. You ever gone to? How many people have gone gambling in Monte Carlo? Okay, I'm impressed again. How many people have been in Monte Carlo? Oh, that's cool. Is it cool? Yeah, I've heard it's nice. Okay. The probability of the ball landing 26 is 1 out of 38. Okay. What's the probability of the ball landing in red? Well, huh? Yeah, 18 over 38. You just simply count the number of red holes, right? And there, I think, there's like other 36 numbered ones, half of them are red, yeah, because there's 18 of those. And so there's 18 over 38 is probability. Makes sense? Okay. So the probability of ball landing in red is 18 over 38. What's the probability of ball landing in numbers 1 to 12? 12 over 38, yeah? It's 12 holes. Each one has 1 over 38 probability landing in it. All right, makes sense? Just probabilities. All right, that's my roulette wheel again. This is the little board. If you actually play roulette, you put your chips on these things. Right? You've seen these in like James Bond movies or whatever. Okay. All right, let's see. If I put $1 on red, what is my average payout? Okay, so put one of my chips on red. That's your chip on that little guy there. Okay, what's your average payout? Okay, well, do you know the odds? So, okay, if I put a chip on red, and if I win, how many dollars do I get back? I get 2 back. Seems like right? I get the original chip plus another chip. That's what I get if I win. Right? That's true, I think. If I lose it, how much do I get? Nothing. Make sense? Okay, so on average, what is my payout? Well, how often do I win? What's the probability I win? 18 over 38, right? And that's multiplied by what? 2. Does that make sense, right? 18 out of 38 times I get 2, right? And then what's the probability I lose? 20 out of 38, and out of those times I get what? 0, right? So it looks like this. The probability of red I win is 18 out of 38. The probability of some other color, that is I lose, is 20 out of 38. If I win, I get $2. If I lose, I get $0. So overall, I'll get 2 times 18 over 38. That's what I get if I win, times the probability I win. Plus 0, which is what I get if I lose, times the probability of losing. Yeah? Makes sense? Also, altogether, that's 36 over 38. That's overall, if I pay it many thousands of times, this is what I'll expect to get. Makes sense? 18 out of 38 times, I'll get 2. 20 out of 38 times, I'll get 0. That number altogether is 36 over 38. Makes sense? Okay. Why is that number less than 1? Yeah, this is how the house makes money. Yeah? If that number were bigger than 1, then the house would be losing money. Yeah? Huh?
Not too bad.
The house makes a lot of money, yeah, 5%. It's a very good take. Okay. It's like the best business in the world. It's like guaranteed 5% all the time. Okay. Does that make sense? Okay, let's do some other ones. Okay, so the expected value is this thing, 36 over 30. That's the name of this thing. 36 over 30. Okay. This is our definition. The expected value of a gamble is the probability of the event times the payoff from that event, summed up with all of them. Okay, so if you've got a bunch of like, if you're exposed to lots of random things, the expected value over that thing is the probability of the thing times the payoff from that thing, summed up overall. Okay? That's the expected value. Okay. So the expected value of betting on red is 36 over 38. What's the expected value of betting on 26? We showed it to you, but if you put your chip on one number, what's your payout? That's a very risky gamble, right? But how much you get a lot? I mean, you know what you get? I think you get 36 back. If you put a chip on a single number and you win, you get 36 back.
You get the amount.
Huh?
Like if you put it on 26 and you put $1, you get $26.
No, I don't think so. Then why would anybody put on 1? Right? Yeah. I think it's just 36. Yeah, I think it's right. Okay, so if I win by putting on a certain number, the probability I win is from putting on 26 is just 1 out of 38, right? That's the probability the ball lands in that little hole. But I'll get a large payout of 36 if that happens. The probability I lose is 37 over 38. That's multiplied by 0. Okay, that's my expected value. Make sense? Sometimes people ask me, do I have to know anything about gambling to take this class? I say, no, you don't. Although a lot of probability theory actually originally came from gambling. That's where it all started. That's why we have the mathematical topic of probability theory. Okay. What's the expected value of betting 1 to 12? Okay, so if I go back, let's just see. I can put my number on that first 12. I can put my chip on that. Okay. If I win with that, I think I get it. If I put a chip and I win, I get 3 chips back. Okay? Make sense? That's a slightly, yeah? I think that's true. Okay.
Like 2 additional chips?
Huh?
2 additional chips?
Yeah, exactly. You get your chip back and traditional. Okay. All right. So I put it on 1 to 12. The probability of that winning is 12 out of 38, I think. And I'll get 3 chips back. Okay. The probability I lose is 26 out of 38, and you get 0 chips back. Okay. And that's also 36. That's expected value. Makes sense?
Can
Yes.
you explain, for the expected value of betting on 26, why the 1 out of 38 is not 3 out of 36?
Okay, because this is what the house gives you. This is like, they will say, if you win by 3 chips on 26, if you win, you get 36 chips back, plus your original. No, okay, not plus your original chip, it's 36 back. Yeah. So it's a good deal if you win, right? Because you put 1 chip and you get back 36 if you win. Makes sense?
What is that number?
It comes from the rules of roulette, I guess. I just looked it up. Do you want me to look it up? Or do you
No.
know?
I just want to know if it was like included or kind of arbitrary.
Well, it's not completely arbitrary
Yeah,
because
to them.
yeah. I mean, for example, they wouldn't want to make that number 50 or something like that. That would maybe it's not a big deal for them.
Yeah.
Okay. Yeah, this makes sense. Yeah.
I just don't totally understand for both of them,
Uh-huh.
the plus 37 over 38 or 26 over 38 times 0. Is that something else?
Yeah. So
Is that how you set up all of the
okay, the expected values again will probability of each event times the tail from each event, summed up for all events. So whenever I make a gamble, I either lose or win. Right? So this is the probability I win if I put it on something. This is the probability I lose. Okay.
But when you do it, when you make it times 0, it just ends up being 0.
Yeah, that's okay. Yeah. So that this means that if I lose, I just get 0 just now. If I got, for example, if they said, well, if you lose, in addition, if they pay 5 more chips, then it would be like a -5. Okay. All right, so let's do another one. How about today there's a 20% chance of snow, 50% chance of rain, and 30% chance of no precipitation. And say that my payout from snow is 10, my payout from rain is -20, and my payout from no precipitation is 0. Okay. So what is my overall expected value going to be? Well, with 20% probability of snow, my payout from snow is 10, so it's 20% times 10. So 50% chance of snow, and if my payout from rain, 50% chance of rain, my payout from rain is -20, so it's 50% times -20. There's a 30% chance of no precipitation, my payout from no precipitation is 0, so that's what it is. Make sense? You simply just take the probability of all things, multiply it by the payout you get from that thing, and sum it all up. So that's expected. Make sense? Another way to think about it is, sometimes I'm getting a 10, sometimes I'm getting -20, sometimes I'm getting 0. Well, my overall payout from those things depends on how often those things happen, right? So sometimes I'm getting a 10, how often? Well, 20% of the time. Okay? Sometimes I'm getting a -20, how often? Well, 50% of the time. Sometimes I'm getting 0, 30%. So I add all this stuff. Okay?
I have a question about the roulette example.
Sure.
Why do you not count what you have to start with?
Oh, okay, so I did this as, these are, in those calculations, it was not a net, right? It was just like a gross, like receipts. So you might say, well, okay. Okay, so like, in this case, I got 0.95, so if I put a chip in, 18 out of 38 times I get 2, 20 out of 38 times I get 0, so it all becomes 0.95.
Right, but you have to start with $1, so
Yeah, exactly,
does
right.
that affect your payouts though?
Yeah, of course, right. So if this is what I'm buying with the dollar, Right? I'm buying, if I buy something with the dollar, I get this thing, right? But overall, it's bad for me, right? Because I'm getting expected value of 0.95 and paying $1 for it. Yeah, so this is not net, this is the gross, this is like revenue, not profit. Yeah? So if it was net, then this would be a negative number. Yeah? It would be like, with 18 out of 38 probability, I will gain 1, right? With 20 out of 38 probability, I will lose 1, right?
Right.
And then that would be like negative 0.05. Any questions about that? Okay, so what's the point of all doing this? The point of doing this is simply to be able to fill in those numbers. Okay, so let's work on that. So let's see. So my keeper is red. So here's my keeper, and the keeper can either go say east or west. Can you see that? Probably not, right? No. Well, there is black. Right? Okay. Here's my keeper. Go east. Go this. Now my striker, I'll do it with go east. Okay. All right. Let's try to fill in some of these numbers. Okay. How do we fill in the payoffs? Okay. Oops, that's the answer. How do we fill in the payoffs? Okay, let's do them one by one. Say that the keeper, we'll do that one right there. So say the keeper's doing 50-50. So the keeper's going half the time over here and half the time this way. Okay? And the striker's going east. Okay, so the striker's going east. Okay? So you see, is it clear what I'm doing? I'm trying to fill in that little number there. Okay? I'm trying to fill in the payoffs for in that space. So this is where the keeper goes 50-50 and the striker's going east. Okay? All right. So, let me show right down my original pages. Keeper goes east. Striker goes east. Okay, so this is. Okay. So what's happening is the keeper's going half the time playing here, right? Half the time playing here. And the striker's playing east all the time, so I'll put a big one there. Okay? See what I'm doing? Okay. So half the time the keeper's going east, half the time the keeper's going west. The striker's going east all the time. Okay. So what's the expected utility or the expected value for the keeper? So I'll write down this expected utility for the keeper. The EU means expected utility. Okay. Keeper means keeper.
Is expected utility the same thing as expected value?
Yeah, expected utility. I'm sorry. Yeah, expected payoff. I could put EV if you want. Let's say expected payoff. Okay, what is expected value for the keeper? Well, the keeper is either getting a 1 or a 0, right? How often is the keeper getting a 1? Half the time, right? So the expected utility is going to be half times 1. Yes? Sometimes the keeper is getting a 0. How often is that happening? Half the time too. Plus half times 0. See? The expected value is simply the probability of each thing times the payoff of each thing summed over all things. Make sense? What is this number? Half. That's 5. Okay, how about the striker? Okay, half the time, so we're either here or here, right? Half the time the striker is getting what? 0, right? Half the time the striker is getting a 1. Right? So this number is also 0.4. So let's fill that in. Okay. Does that make sense, what we're doing? Yeah? It makes sense, right? If the keeper's going 50-50, the striker's going east all the time, right? That means basically half the time the striker wins, half the time the keeper wins. Yeah? Okay. Let's do some more. How about that one up there? This is where the keeper goes east all the time, the striker goes 50-50. Here the keeper's going east all the time. I'll put a 1 there. And the striker's going 50-50. Okay. So now, keeper's doing this all the time, like 1. Okay. Now the striker's doing 50. What's the expected value of the keeper? So half the time we're here, half the time we're here. Yes? Okay, so half the time the keeper's getting a 1, half the time the keeper's getting a. Okay, how often does the 1 happen? I just said I guess half the time, right? So half the time the keeper's getting a 1, half the time the keeper's getting a 0. Right? So this number is. How about the striker? Half the time the striker is getting a 0. And half the time the striker is getting a 1. So this overall expected value is going to be what? So let's put it in 2. Okay, does it make sense what we're doing? Do you want to just, no? Does it make sense what we're doing? What's the question? Yeah, first of all, so what's the motivation? Why don't we just do this? Because there's no Nash equilibrium, right? So we want to make a prediction, and what we actually see people do is what? They randomize, right? They actually randomize this. So that's why we have to add randomized stuff. Okay? Yeah.
Is there no Nash equilibrium because it's random?
No. Right?
Or it just happens?
This is just, there's nothing's wrong with this game. It just happens to be no Nash equilibrium in this game. So we kind of have to, so one way to think about it is, in this game, there's no stable thing in some sense, right? It's not like I'm going to go east all the time, I'm going to go west all the time. We always want to change. Okay, so people actually randomize, so we're going to have to consider randomization. So that's why I threw in that 50-50 strategy. Okay? That's why I put that in there. Is it clear why I put that in there? Right, I had to in some sense, right? Because that's what actually people do. They actually randomize. Okay, then when I put that in there, then I have to think about what these payoffs are going to be. Figure out the payoffs, I have to do that expected value calculation, right? I have to figure out what your payoffs are from a random thing. Yeah? Make sense? Okay. By the way, this is kind of the hardest thing we'll do in this class in some sense, technically, all right? So some people don't teach it. I like to teach it because I think it's interesting, but this is the hardest thing in some sense we'll do. So it won't get harder from here too much. Yeah.
I didn't really understand what's the difference between the table and the 50-50.
What do you mean? Between this table and there? Oh, this is just a game with another strategy in there. So I'm adding a new strategy. So instead of person have 2 strategies.
I just feel like 50-50 strategy is just like that.
No, it's not quite the same. Because here, you can go either east or west. Right? Choose east or west. When we see this game, people don't either play east or west. Rather, they randomize between them, which is like a different strategy. Right? Does that make sense? Yeah? People are, like, if you're in this game, you would never just play east all the time. That's the shortest thing. You'll never play west all the time. You'd want to randomize. So to analyze that, we have to include randomization as a strategy. That's all I'm saying. Okay, yeah, so you're right. I'm not really changing the game. Actually, I'm not changing the game at all. I'm starting with this game and adding another strategy in there. I guess maybe that's clear as saying. I'm adding the randomized thing. Okay? Yeah?
For the expected values for the keeper,
Uh-huh.
so I was using the 1 to 0 that's on the
Yes.
east side.
Yeah. We use the numbers here in the original.
Or I just need for, or can you just go over how you got the numbers for?
Okay, so this is where the keeper's going east all the time, the striker's going half the time east, half the time west. Okay? If the keeper's going east all the time, then we're either in this or this. Yeah? Okay? So the keeper going east all the time, the striker's going this half the time, striker's going this half time. So half time here, half time. That's all. So,
How does that, equal the keeper's, expected value?
okay, so don't worry about expected value for now, but just realize, right? It makes sense that half time here, half time here. Yes? That's clear, yes? Okay. What is expected value for the keeper? Well, half the time the keeper's getting 1, half the time the keeper's getting 0. That's this. So, makes sense? Yeah. Huh? Yeah, we will do that in a second. But is it clear what we're trying to do? That's all I'm trying to get you to do. Okay? Any more questions? Yeah, we will do some. Huh?
In regards to we talk about time, we do the half the time. Is that in regards to the amount of strategies available, or which, or the half that you're getting for the parentheses?
I can do this, sir.
The half you're getting for the parentheses.
Right.
You're talking about time. Where you, let's say there's a game with like 3 strategies, 4 strategies.
Oh, yeah, yeah, okay. So if it's a more complicated game, this would be a more complicated thing. Yeah. If you had 4 strategies here, you'd be like 1/3, 1/2, 1/6, or something like that. It would be a 1/3 half, or something, 1/2, so it would be a long thing. Okay. Just for now, is it clear what we're doing? Yeah? All right, so let's see. So I think we figured this out, right? What's the payoff here for the keeper? If the keeper goes east all the time and the striker is 50-50? Oh, what did I, oh, I'm sorry, I wrote it down. I do, it's over here. Yeah, we put it already. What goes in here? Do you want to do this? It's pretty clear. It'll also be half 50-50, right? 0.5, 0.5, yes? How about here? Same thing. Okay, the only thing which is slightly different is this one in the middle, okay? So this is where the keeper is going half-half. Half the time east, half the time west. And so is the striker. So striker is going half the time east, half the time west. So keeper. Okay, so now if both people are randomizing half-half, what's the probability of this event occurring? They both go east. Is it 0.5? It's 0.25, right? It's a half times a half. Make sense, right? So if we keep it going east half the time, west half the time, strike it going east half the time, west half the time, with probably half times a half, 1/4 will end up here. Yeah? Okay, so the keeper gets, with probably a 4th, the keeper gets a what? A 1, yeah? What's the probability this happens? Also a 4th, yeah? What's the probability this happens? Also a 4th. The probability this occurs as well. Also a 4th. Make sense? This is a little more complicated because all 4 things can happen. Each one's happening probably before. Okay. So what's this number? This is a 4th plus a 4th. This number is what? Okay, let's do the striker. The striker, this happens with a probably 1/4. The striker gets what? 0, right? This happens with probably 1/4. The striker gets a 1. This happens with probably 1/4. Gets a 1. This happens with probably 1/4. It's a 0. This number is 1/4 plus 1/4. Just look at that. Are we okay? So this is always slightly more complicated, but still we can do it, yeah? Okay, so if I'm randomizing half-half, you're randomizing half-half, each of those things happens with probability 0.4, and I can just sum up and add up over all those things. Okay, you with me? Yeah.
Why did you account for all 4 of the strategies in that one, but not for the other ones?
Oh, okay, the reason is because this time if I'm randomizing here, you're randomizing, all 4 things are possible. Right? Okay, but before, like when I did that one, okay? So that one, when the keeper was going east all the time, okay, let's put a 1 there, but then only 2 things ever happened. These things never happened, so I didn't have to do that whole thing. I just did a half here and a half here. That was it. See what I'm saying? Any questions? You okay? Okay. You're okay? I don't want to stop you. But just again, if you get confused, think about the original motivation, right? The original motivation, there was no Nash equilibrium in the original game, so we have to include randomness. Once you conclude randomness as a randomized strategy, then you have to think about what the payoffs are for the strategies, right? And that's what we did. Yes?
Is the randomness always going to be 50-50 if there are two options for each
No.
player?
So this is an easier example, but it will not always be 50-50. Anyway, so what goes in here, we just figure this out, right? And this middle one, it's also 0.5. Okay, so here we go. This is our game. So we started with the original game, no Nash equilibrium, so we added randomized strategies, the 50-50 strategy, and then we figured out the payoffs in each. Now we have this game, because it's sort of an expanded game. Okay. All right. Okay. So we have this. Let's find Nash equilibrium of this game. Let's do our little stars and things. If striker goes east, what's the best response for the keeper? East, right? 1 is the biggest number. Do you want to do the underlines or the stars? Underlines? Oh, I don't know, all the stars. I like the stars. If the striker goes 50-50, what's the best response for the keeper? All of them, right?
Does it matter if we underline or?
It doesn't matter. I think underlining is a little clearer. I mean, it's just easier, but whatever. I'm doing the stars here because I'm going to use stars again in a second. Okay, if the striker goes west, what's the best response for the keeper? West, yeah. If the striker goes west, the keeper wants to go west. Okay. How about this? If the keeper goes east, now what's the best response for the striker? West, right? The striker wants to go where the keeper is not. If the keeper goes 50-50, what's the best response for the striker? All of them. If the keeper goes west, what does the striker want to do? East, right? Because 1's the biggest number. Okay. So, do I have a Nash equilibrium? Yeah, it turns out I do. I do. This one right here. Okay. So, when I added my new strategies, I added the 50-50 strategies, I was able to find this Nash equilibrium, where both people do 50-50. If I were to write it as a sentence, it looks like this. In the Nash equilibrium, the keeper goes east with probably 0.5, west with probably 0.5. The striker goes east with probably 0.5, west with probably 0.5. Okay? Yeah,
So you only use randomization when there's no Nash equilibrium?
that's a good question. In this case, we had to in some sense, right? But actually, there are cases where there are existing Nash equilibrium, and then we'll go, what we originally call Nash equilibrium, called pure strategy Nash equilibrium, is non-randomization. So there's ones in which there are pure strategy Nash equilibrium, but there's also a randomized one in addition. So yeah. So we'll do exactly that. Okay. Any question what we did? So in some sense, we succeeded, right? There was no Nash equilibrium in the original game, so we added random strategies. And it worked. And does this make sense that people would do this? Yeah, people actually, this is a pretty reasonable prediction, right? People do randomize half-half, right? So let me ask you, why don't people randomize 52%, 48%? Why do they randomize exactly half-half? Yeah.
In the long term, the more they randomize it eventually.
Yeah. Well, I mean, no. Say that you're playing this game all the time, but you tend to go for east 70% of the time, west 30%. That can be good for you. No, why?
Someone figured it out.
Yeah, exactly. You get the scanner report will come back, the people say, oh, best record goes 70% east, so the goal is okay, sure, I'll play it. Right? You actually, so if it's 70-30, that's not a good thing for you, right? How about 52-48? Still not that great, right? Because they'll cover the side which you'll favor, right? So actually, you want to be as close to 50-50 as possible, right? You want to be as, right? Does that make sense? Yeah. Okay, so this sort of makes sense. Okay. All right. So what do we do? Again, this is original situation to review. There's no Nash equilibrium here. Okay, so what do we do? We added the 50-50 strategy, okay, and we got this Nash. Okay. So somebody asked us already, is this always going to work? Is this 50-50 always going to work? In some sense, you lucked out, right? What about, we didn't consider like lots of other things like 52-48 or 30-70. There's actually lots of ways you can randomize it. Okay. So there are lots of other randomized strategies too. We just happen to luck out here, but we might not luck out in the future. How do I solve this for general gains? Any questions? Okay. How do we include all possible randomized strategies? So not just 50-50, but like 17-83. All these things. Okay. Well, what we'll do is use a little bit of math or algebra. We'll say that the keeper goes east with probability P and west with 1 minus P. These numbers have to add up to 1 because of probabilities. The striker will go east with probability Q and west with probability 1 minus Q. So, Q. Okay, and we'll basically do the same thing, but we'll let P and Q vary freely. Okay, so people will go east with probably P and west with probably 1 minus P. That's what I'm doing here. The striker will go east with probably Q, west with probably 1 minus Q. That's what those little numbers mean. All right, so then, move on. The game with all possible randomized strategies looks like this. Well, it looks like some really large box kind of thing. What I'm doing is, so before there were 2 strategies and then a third, but actually there's like hundreds or thousands or millions, right? There's P equals 1, P equals 0.99, P equals 0.98, et cetera, right? You can think of this as like a huge spreadsheet of numbers, right? Every single possible randomization is going to be on this side. So what I mean here is P equals 1 corresponds to the keeper going east all the time, because that's 1 and that's 0, right? P equals 0 means that when P equals 0, this number is a 1 and this is a 0, right? So that P equals 0 means the keeper goes west all the time. That's where the keeper goes east all the time. That's where the keeper goes west all the time. And 50-50 would be kind of like that. Does that make sense? In this little table. This will be like P equals 0.7 means the keeper goes east 70% of the time, striker, and the keeper goes east 70% of the time, west 30% of the time. See what I'm saying? There's like lots and lots of little rows in here. Okay. How about the striker? Q equals 1 means the striker goes east all the time. Q equals 0 means the striker goes west all the time. Okay. Okay. So I just have this really, really huge matrix, huge table. Okay. And Q is kind of like a parameter for my strategy. So, for example, if P is 0.7 and Q is 0.7, I'm going to have to fill in some numbers there. How do I fill in all the payoffs? Okay. Do I want to do that? No, I do not want to do that because that would take a long time. I can show you in a spreadsheet I have it somewhere. You want to see what it looks like? I think I have it somewhere. Yeah, you see that? So it's kind of, see what I'm doing? We'll just look at it and then forget about it. See, P is going from 1 to 0 and Q is going from 1 to 0 up here. And this is person 1 strategies. So the person 1's payoffs. I put them in there. Yeah? So I kind of want to avoid doing this as much as possible. Right? See what I'm saying? So that's what it would look like, right? Okay. All right. I'll put this on the website to see. Okay, anyway. Okay, so again, this is my thing. Do I want to put the payoffs in there? How do we fill in the payoffs? Too much work. We're not going to do that. Instead, We'll just fill in the best responses, the stars and the pluses. Okay, so we're not going to write down the payouts, but just the best
So
responses.
is this like an infinitely large?
Yes, it is.
game?
Exactly, right. Yeah. So we're not going to analyze infinitely large things. Rather, we're going to cut to the conclusion in some sense, okay? All right. So in other words, we're not going to write to the payouts, we're just going to do the stars and pluses. Does this make sense? Okay. So let's do the keeper's best response in my thing. Okay. So I'm just going to do the stars. If the striker goes east, the keeper can choose anything in here, right? Which will be the keeper's best response if the striker goes east all the time? East all the time, right? So if you're going east all the time corresponds to that little thingy there. So I'm going to put a little star there. Okay? That's the best response. That's the thing which has the highest payout for the keeper among all these things. Okay. What if the striker goes west? What is the keeper's best response? Go west, right? That corresponds to that one. Listen. Of all the things in here, the best thing for the keeper is that one. Okay, so let's put a little star there. Okay. What if the striker goes east 99% of the time? What's the best response for the keeper? The keeper will go east, right? All the time. Okay. Because if the striker is going 99% of the east, people just go to Make sense? What if the striker goes west almost all the time? Like 99% of the time. What is the keeper going to do then? West. Make sense? Okay, what if the striker goes east 90% of the time, like around there? What is the keeper going to do? East, right? Okay. What if the striker goes west 90% of the time? What is the keeper going to do? West, right? See what I'm doing? So let's think about it this way. The striker goes east all the time, the keeper goes east. Striker goes east 99% of the time, the keeper still wants to go east. Striker goes east 90% of the time, the keeper goes east. What if the striker goes east 80% of the time, 70% of the time? Still go east, yeah? It'll still stay to the side which is most likely, yeah? Okay? So it'll look like that. Okay, so the striker goes east 70% of the time, 65% of the time, 60% of the time. What about 60% of the time? Keeper will still do what? East, right? What about 51% of the time? Still go east. So as the probability the striker goes east, so it goes from 199, 90, 80, 70, 60, 65, even at 51%, it'll still be east, though. The keeper still will want to go east, yes? At what point, though, does the keeper want to go west? Just goes over 50. Make sense? Right? Okay. Okay, so what is that going to look like? That's like 55, whatever, 52. And that's like on the other side. At some point, exactly when Q is 0.5, exactly when the striker is going 50-50, then the keeper will switch over from playing east to west. Does that make sense? Okay, so what is that going to look like in my diagram? If the striker goes east, exactly 50, so east half the time, west half the time, exactly Q equals 0.5, what's the best response for the keeper? So the striker is exactly a randomized half-half. Huh? Well, half-half will be one, but also going east all the time will also be going more west all the time. Right? So if the striker is going half-half, if I cover east all the time, I'll win half the time, right? If I cover west all the time, I'll win half the time. And if I randomize, I'll also win half the time. Make sense? Okay, so if Q goes 0.5, what is my best response? Anything. Okay? It's going to look like that. Right? If Q is 0.5, then I can, no matter what I do, I'll have, if I cover one side with the good and public half, or the other side with the public half. And anything I do, that will. Make sense? Okay. It's a little cold. Okay. Does it make sense? If this is the best response curve, these are where my stars would be if I looked at all the numbers. Okay, that's the keeper's best response. Questions about that? I'll call that 0.5 the switchover probability. That'll be the answer. What about the striker's best response? Okay, very similar. Now, how's it going to work? If the keeper goes east, what does the striker want to do? West, all the time, right? So I'm going to put a little plus there. If the keeper goes west, what does the striker want to do? East, right? If the keeper goes east 99% of the time, what does the striker want to do? With all these numbers, which is the best? West, all the time, right? You see that? Okay. So we're going to have the same picture. When is the striker going to switch over from going from west to east? Exactly at 50%. Okay. So it's going to look like that. When p equals 0.5, it's going to look like that. And this is what the striker's best response looks like. Okay? All right. So how do I find Nash equilibrium? Well, this is my keeper's best response, and this will be a swastika. So there's no way to avoid doing this. So at least I made the arms go in the counterclockwise. Also, swastikas were part of Anasazi and Mayan religions. So anyway, just like it. So that's what's going to happen. The Nash equilibrium is in the middle. Yeah, that's the thing we can still do. Okay, so the first thing is, the very first thing we did when we just did 50-50, when we did that for speculation, we got 50-50 for both players is the Nash equilibrium. Well, we did it the same way this time, yeah? And we did it in a more complicated way. But here, at least we considered every single possible randomized strategy, like an infinite number of this is what we do. Does it make sense? So that's the Nash equilibrium. And if you were to write it down, I didn't have no space, but it's always keeper goes east to probably 0.5, west to probably 0.5. Striker goes east to probably 0.5, west to probably 0.5. So this is how you would find the Nash equilibrium if you consider all possible variables. Any questions? Yeah.
Another would be different if it wasn't the sorry. If p is equal to 0, like p always has to be between 0 and 1. But if the payoffs aren't here like 0 and 1,
Yeah, it would be different, sure.
it would be different numbers, right?
Yeah, so the next question would be something like, we did it for this game, but what about general games? Like, what if this were a 4 or something like that? Would it be different? How do we figure that out? Yeah.
We put it to division.
Yeah, we'll do that in a second.
Be like 1/2 times 1 and 1/2 times 4.
Yeah, exactly. You have to figure it out. Yeah.
Why would it not be 2 diagonal lines?
Oh, this thing here?
Mm-hmm.
So, like, okay, 2 diagonal lines would be your best response?
Well, the Nash would still be.
Oh, yeah, that's interesting. Right. For example, say that this blue thing were like this, and the red thing was like this, and the other thing. The reason is because the diagonal line would not correspond to an actual best response. It was because, like, say, let's do the striker's best response. If the keeper goes east, the striker does really want to go west all the time. If the keeper goes east with probably like 99, the striker doesn't want to go west with probably 99, but wants to go west all the time. Okay? And it's a little non-intuitive, right? You think if the keeper goes east 99% of the time, so 1% of the time the keeper's going west, right? If you're the striker, you'll go for the west all the time. But you might think, shouldn't the striker go west, like maybe east some of the time, right? You would think. Like, okay, so the keeper goes east 99% of the time, west 1% of the time. If I'm the striker, do I ever want to kick to the east? No, right? I will just hit west all the time. Yes? You might think, well, if the other person is randomized, maybe I should, but no, maybe I actually wouldn't do that. So that's why it looks like this. Yeah? So in fact, even if p equals 0.53, you still want to go west all the time. That's why it has this kind of character of switching completely from one to the other. So if it was diagonal, it would be kind of a more gradual thing. When I teach in the next class, like the 6th quarter, we will do games where the best responses are not. Any questions? Remember what we did? Oh, look at this diagram. Also, just look back. Okay, let's see. If I look at, where is, oh yeah, see? Notice, this is my original one. It's still basically the same pattern. You see the best responses. It has that kind of boop, 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 like that. And then that's one's best response and two's best responses like that too. Okay? It's the same thing, yeah. Okay. All right, let's see. Let's do an example now. How about this game? Okay? Let's try to solve this game. Okay. Did you want to do the voting thing?
Yeah.
Oh, hold on. Maybe can you give us how much time do you need?
Probably like 10 to 15 minutes.
Okay, maybe you'll, so we're doing this voting. Has anybody not registered to vote here?
But if you guys need to change your address or move since you last registered, though, like more, right?
Okay. So we will spend a little bit of time since this election is very important, like all elections. So we'll spend maybe 10 minutes or less. So maybe can you give me 5 minutes or so? Okay, thank you. All right. You realize that your generation votes at a much lower percentage than everyone else? You realize that? It's a problem. Okay. All right. Okay. All right. Let me just motivate this up here. Let's see. Is there any other pure Nash equilibria here? If 2 plays A, what is 1 going to do? What's the best response? 4, right? That's a 4. Yeah. I'll do it underline this time. If 2 does B, what's 1's best response? 6. If 1 plays A, 2's best response is 3, right? If 1 plays B, 2's best response is A. Do I have any Nash equilibria? No. So then what do I have to do? I have to do that randomization thing. Yeah? Okay? All right. So how's that going to work? Okay, well, I'm going to put a P up there and a 1 minus P up there. And a Q there and a 1 minus Q up there. Okay? Yeah.
Does anyone have like those buckets with the...
Oh, yeah, thanks. Yeah. Has it not gone round? Where are the buckets? Oh, gee.
I need wine mix. Whatever they do.
Where have the buckets not been? In this area? Oh, come on, people. Okay. Anyway, so, okay. What do we do in this game? We do probabilities, okay? So we'll do this thing. Okay, so next time we'll do that. Okay, so let's do the voting thing. So I just want to say, it's really, really important to vote. It's really important. The sooner you guys get the power, the better off we'll all be. Seriously.